Okay, thank you very much, and also a warm welcome from my side. As you already mentioned, my name is Remo Schäppi. My current affiliation is with MIT in the Department of Mechanical Engineering. However, the work I'm going to present today and talk today is work that was performed back at my time at ETH in Zurich, Switzerland, in collaboration with Professor Otto Steinfeld. And we thought it might be a very nice audience here to bring this to this slightly broader symposium here at MIT. So thermochemical fuel production from sunlight and air. I'm going to talk today about a technical demonstration that we have done in Switzerland under the rooftop of our university, and you already see in the background an impression of how that system looked in real time. The other slide, yeah. Later. Yeah. So a little bit of motivation, fuel production. How do we currently typically do this? Everyone knows this. We take the crude oil out of the earth, we stick it into a refinery to produce our liquid fuel, which we then burn, combust into, for example, the transport sector, which then releases CO2 in the air. So the one-way street in an audience like this, I don't need to talk about the issues that comes with. And the questions we'd like to address is how can we make this carbon-free? How can we tackle this? And when we look on the left-hand side, there are options with EVs and so on, but at least for the aviation industry, to get away from liquid fuel is not an option, at least in the midterm future. So the question we really asked ourselves is how do we get the CO2 back out of the air and back into our fuel? Or in other words, how do we get from up there back down here without the fossil part, but for example, powered by sunlight? Because if we remove the fossil part out of this equation, our fuel is now a renewable fuel powered by sunlight, and is a CO2 neutral fuel, because upon combustion on the left-hand side, we only release as much CO2 in the atmosphere as we previously captured out of the air on the right-hand side. Another benefit of this technology is that the fuel we produce is chemically nearly identical to the current fuel, for example, kerosene. So we can use the existing infrastructure, the existing technologies. We don't need new pipelines, transportation, and so on. We can use the same planes, and it's a drop-in fuel, so we don't need to replace it in one go. We can just slowly but steadily increase the share of this renewable fuel into the current fossil fuel. So what we've done is we demonstrated this entire process chain to solar fuels from sunlight and air on the rooftop of our university. And we've done this by integrating 3 thermochemical process units. First, we have a direct air capture unit that captures CO2 and water out of the ambient air, which we then feed in our solar redox unit. That's the core unit that we developed and did our research with, where we use concentrated sunlight to heat up our reactors and transform the CO2 and water into CO and H2, so-called syngas, which we can then feed in a gas-to-liquid synthesis unit to then condense out our solar fuel. So I'm going to give you an idea how we set that up and show you also some results of how this works. But first, where did we build it? I mentioned already we built this on the rooftop of our university in Zurich. The building on the very left-hand side, that is the main building of ETH in Zurich, and you see like the trams going down the road in the middle, and we literally built this kind of outside under real fuel conditions. What we can see is also, again, the 3 main units, the CO2 capture unit in white, CO2 buffer storage tank, then the solar redox unit, the core unit, as this big parabolic dish set up there. The gas is then going inside the lab where the whole system is controlled, it's analyzed, come back outside to be compressed, to then be processed in the gas to liquid synthesis unit back inside the lab. And you can see that we demonstrated this entire process chain in an area probably less than 10 by 10 square meters in the middle of the city of Zurich. Now let me look at this a bit more schematically. We can again see the three main units, the direct air capture unit on the bottom left in green, then solar redox unit in yellow, and the gas to liquid synthesis unit in blue. So first we capture the CO2 and also water, very importantly, out of the ambient air. This is done through a sorbent packed bed reactor running an adsorption-desorption cycle based on temperature and pressure swing. CO2 is compressed in an intermediate buffer storage tank. Water is stored in liquid form. We then feed both through a steam generator into our solar reactors installed on the solar parabolic concentrator. And this is, as I said before, is the kind of the core unit of this process, dominated by this nearly 5 meter diameter parabolic dish concentrator that automatically tracks the sun at all times during the day based on mathematical curves and a solar sensor. And we use this to concentrate the incoming solar radiation to then reflect it on this flat planar secondary mirror that you can also see at the right hand side here and flat here. So the incoming solar radiation is concentrated, reflected, and focused on our instruments on the dish. We currently have 4 instruments installed, a so-called water conversion target to do flux measurements, a water calorimeter to measure the input power into our system, and then the 2 solar reactors on the left and on the right hand side. This optical system allows us to reach concentrations exceeding 5,000 suns peak or exceeding 2,500 suns average over the 60 millimeter aperture of our reactors indicated in the white circle. How does a solar reactor look? It's basically an Inconel shell with aluminum insulation, sealed off with a radiation shield and a quartz window. Sealing this reactor with a quartz window allows us to run the reactor also under a pressure swing and evacuation. And then the core of this reactor, the heart of the reactor, is this called Seria RPC, reticulated porous ceramic. That is a foam-type ceramic structure developed in our lab that comes in a dual-scale porosity. So we have pores in millimeter scale for enhanced radiative heat transfer and pores in micrometer scale for enhanced mass transfer. The Seria RPC is made out of pure cerium redox. What we now run in this reactor is a so-called reduction oxidation cycle. So we first have a reduction phase where we heat up the reactor up to 1500 degrees Celsius, and the Seria, the RPC, releases oxygen under reduced pressure of down to about 10 millibars. This is then followed by oxidation with CO2 and or water, where we transform CO2 and water into CO and H2. This is typically performed at ambient pressure and at lower temperatures of maybe below 900 degrees Celsius. After the reactors, the produced syngas is then fed downstream, where it's hooked up either to a vacuum pump for the reduction phase or through the gas analysis, and then back into the gas to liquid synthesis unit in terms of the oxidation phase. Gas to liquid synthesis unit, this is basically an off-the-shelf reactor that we added on for a purpose of demonstration, a packed bed reactor running the top row catalyst, where we can condense out our liquid fuel with a given temperature and pressure. Now, what I want to point out, since we also included a recycling loop down here, it is really important to control the quality of this syngas entering the gas to liquid synthesis unit that is actually suitable for the synthesis unit. So we can really need to tailor this composition here based on what we feed into our reactors and at what temperatures and so on. Here I'm going to show an exemplary cycle targeting syngas, in this case for methanol synthesis. So we're talking H2 to COX, a CO plus CO2 ratio between 2 and 3, depending on the catalyst and CO2 conversion. And a characteristic cycle looks like this. So we see the temperature swing in In yellow, during reduction, heating up, in this case, to 1450 degrees Celsius, before we start cooling down and then perform the oxidation. We see in purple the pressure swing, so reduced pressure during reduction in ambient for oxidation. And then we see in blue the oxygen evolution during reduction, as well as H2 and CO evolution during oxidation in red and green. We look at this a bit more closely now, only for the oxidation part, so about minute 30 to the end from the left-hand side over here. We can see what syngas comes out, and we have a closer look at the numbers. And we see that the full oxidation would yield about 18.5 liters of syngas. However, the composition is not really suitable for methanol synthesis, so H2 to CO2 rate of 1.5. Also, the CO2 conversion is very low, especially because towards the end of this cycle, we use predominantly CO2. At the beginning, this is mainly argon. Because of the size of our system, we had some argon in that we wouldn't need in a bigger system, so we would not interested in this first time. And as I mentioned, towards the end is predominantly unreacted CO2. The oxidation reaction comes to an end. However, if we compare to the full oxidation, only capture about minute 2 to 10, after that we would bring the reactor back on sun, we have only about 9.4 liters of syngas. However, the composition is now suitable for methanol synthesis. H2 to CO2 ratio is 2.58, and a CO2 conversion also increased to above 25% cumulative. Now, as I mentioned before, we don't have only 1 but 2 reactors installed on that dish, with the idea that while one reactor is receiving the concentrated solar radiation, performing the solar reduction and releasing oxygen, the second reactor is actually cooling down. We feed in CO2 and water, performing the oxidation of sun, producing our syngas. If both of these reactors finished their individual step, we simply switch the concentrated solar radiation around. Now the first reactor is cooling down, performing the oxidation, producing the syngas, while the second reactor is now on sun, heating up, performing the solar reduction and releasing oxygen. This switching around of solar concentrated radiation, we simply do by turning the secondary mirror. This is a video in real life time where you can see the focal point moving in the mirror from the reactor on the left-hand side over to the reactor on the right-hand side. So this whole system is fully automated and allows us to really just run this full day continuous cycles. This is an exemplary day targeting again syngas for methanol synthesis, where we can now see this kind of forward-backwards gain between the 2 reactors. So we have the temperature curves in blue and red of these 2 reactors. Underneath in the dashed lines, again, blue and red for the 2 reactors, is the pressure swing. And in the yellow curve, we have the DNI, the direct normal irradiation. So this is basically indicating solar power over the day, where we can see increasing in the morning, about peaking around solar noon, and then decreasing again towards the afternoon. So this also shows us that we're now actually performing this outside under real field conditions with real solar conditions, which obviously our reactors need to adapt to continuously, especially solar conditions. And you can see that the cycling towards the end of the day, the cycles get a bit longer with the decreasing solar irradiation. Underneath, we have the syngas composition that we collected over these cycles. So in the diamonds, we have H2, CO2 in circles, CO in asterisks here, and so we can see that even though the solar conditions are changing, the production is very continuous and constant over the entire day. In black, we see the accumulated syngas yield over this day, and if we look at the numbers of these particular 17 cycles, we produce just under 100 liters of syngas with an H2 to CO2 ratio of 2.7, that's suitable for methanol synthesis. CO2 conversion was 21% at this time. Of course, the challenge always is now, how do we increase the solar to fuel efficiency, and what's the efficiency at this moment anyway? So solar to fuel efficiency we define as the calorific value of the fuel divided by the solar power input and some penalties for inert gases, if in case we need some, and pump work mainly for reduction. This current reactor has an efficiency between 1.9 and 3.8%, depending on the solar conditions and a couple of other factors. The highest to date demonstrated solar to fuel efficiency is 5.6. That was on a 50 kilowatt scale reactor. This one's about 6 kilowatts, demonstrated on a small solar tower in the south of Madrid in Spain that we had another project. So how can we further increase this? We can of course work on the parameters, the setups. That's work that been conducted after this work here. I'm not going to go into too much details of that. Then we can really focus and optimize the porous ceramic structure inside. So this RPC is already quite far in development, but there's a lot of potential to further increase by, for example, we have projects with 3D printing the ceramic structure. So it's all participating and really increase how much fuel we can get out of it. And of course, a very important cycle is heat recovery, because you can see we're having quite a big temperature swing. And at the moment that heat is just lost to the environment, but if we can capture some of this heat, that is essential to push the solar to fuel efficiency. And in fact, that's one of the topics that my colleague Peter, who's going to speak after me here, will address in his research here at MIT. Well, we're talking about efficiency of this implemented process change, just to give you a brief, very rough idea. Based on an efficiency of the direct air capture unit, assuming heat integration, measured optical efficiencies and solar syngas efficiencies that I mentioned before. The solar redox unit itself currently has an efficiency between 1.1 and 2.3%. Gas to liquid synthesis unit in efficiency, we estimated about 75%. This is actually an exothermic process, but still you have some recycling losses and so on. And that comes to an overall system efficiency between or roughly around 1%. We estimate that with some improvements and where the technology is going, this could probably go to more towards like 13% or something for a setup or an idea like this, obviously slightly upscale version of it. Now, so far I was only talking about methanol synthesis, so I just wanted to briefly show that we've also done different synthesis, for example, Fischer-Tropsch synthesis, so now really targeting aviation fuels, for example. The cycle looks pretty much the same, so I'll go over this quite quickly, also given the time. So again, we see now, because the target is H2 to CO ratio of about 2, CO2 doesn't matter as much anymore, we can have a much more CO now in our syngas for the oxidation. And we see first on the oxidation side, the CO peak coming first here, then followed by the H2 peak in red. We again look at the numbers, full oxidation, comparable 15.5 liters of syngas, but the ratio is a bit too high, CO2 conversion relatively low. However, again, if we start stopping the cycle after about minute 4.2, which is where the H2 to CO ratio is exactly 2, this is now suitable for Fischer-Tropsch synthesis. And also we can see that by having a little bit less syngas now, but we also increase the CO2 conversion above 35%. So a lot of the work that's gone into this afterwards is obviously how to get more out of this. In other words, how can we shift this gray area further to the right and make more use of the potential of our system? And we run a very in-depth parametric analysis for this. And now I'm coming towards the end of my talk. Of course, we didn't only do one cycle, but multiple cycles over multiple days. Here's an example of 152 continuous cycles targeting methanol synthesis, where we have first demonstrated a very constant ratio around 2, and then changed to a cumulative ratio of 2.5. And we see that over these 152 cycles, 18 days, we have over 1,000 liters of syngas with an H2 to COX ratio of 2.48, suitable for methanol synthesis, CO2 conversion 21%. And this is actually synthesis that we then perform in the gas to liquid synthesis to figure it out. And then we condensed our methanol, and what you see here is the first methanol, the first liquid fuel made of sunlight and air. With this, I'm at the end of my presentation. Thank you very much for your attention. I'd like to acknowledge some of the funding agencies.
Thank you very much. I'll take one question there.
It's very impressive talk. I have two questions. The temperature increase in the reactor usually is very fast, over 30 degrees per minute. Then it requires lots of heating energy. But in your efficiency calculation, I haven't found any energy requirement for heating or cooling. Have you ever considered heating energy?
In the energy calculation here, it's in the kind of Q solar, in the formula would have been Q solar. So that's the solar energy input. So the whole heating is done by the concentrated solar radiation. That's the heat input. Cooling is not needed, so we don't need any cooling. There is a little bit of cooling losses included in the calculation for cooling the spillage and things in front of the reactor, but there's no active cooling. The reactor is exposed to the surroundings and it will cool down. Radiative losses mainly, but also convective losses. So there's no cooling involved of the reactor as such. The heating is obviously accounted for. That's the biggest input into the efficiency calculation by far. It's in the pump work and also inert gas or something. If we have some, it's less than 5%. So it's big input is solar energy.
Very good. Thanks for the question. Thank you for the, let's thank our speaker again. Next speaker is Peter Scott. His title is Design and Modeling of an Indirectly Irradiated Solar Thermochemical Hydrogen Reactor for Use in a Reactor Train System. I'll give you a 5-minute warning. And again, to all speakers, try to allow for time for questions. I appreciate it.